Okay, so I need to give you guys chain rules. There are multiple chain rules. You have to be just a titch careful. Okay? You guys with me?
Yes.
Okay, so say I had some function f of x and y, and say I also knew that x was a function of t and y was also a function of t. You guys see this? So like I have some surface, right? So I'm going to draw my handkerchief again. Here's my surface. And then down here in the xy plane below my surface, right, I have some kind of a function of t that wanders around. You guys see that? You with me? So t is some variable that maybe plays forward. So like there's a point t is 0. Here's a point t is 1. Here's a point t is 2. So we're kind of heading along that way on this curve. You guys see that? I could ask reasonably the question, if you feed that curve into f, how does z change as t changes? You guys see that?
Okay.
So like once I did f to this thing, I would get some kind of like wander around up here curve, right? And there's some change in z that's happening there. You guys cool with this?
Yep.
So I could do something like, okay, what is df dt?
Oh, first you have to replace the x and y.
Okay, so you guys know a procedure to get this if you had some formulas, right?
Probably.
Like, if you knew that this equaled cosine and this equaled 7 pi t plus 3, right? You could take those two things and shove them in for the x and y here and get some explicit f of t function, and then you could play calc 1 with it.
Yeah.
You guys all cool with that? If you didn't want to go to the trouble, you can do this the calc 3 way, which is you would take the partial with respect to x, partial of f with respect to x, and the partial of f with respect to y, and you multiply this one by dx dt, and you multiply this one by dy dt.
And those are not partials?
Yeah, and why aren't those partials? So why did these get hard derivatives and those are partials?
Because the partials for
There's no t direction. That's just a way of synthesizing x and y together.
because it's a partial derivative where it's f given x and ignoring y, and then f given y ignoring x.
Yeah, so this is like the slope in the x direction, right? And then this thing is the
Actual.
change in x per change in t, right?
Yep.
So this thing all told kind of cancels and gives you the change in f per change in t, but it only accounts for the one direction. You guys see that? There's another source of change out there, that's that thing, right? That's also the y direction. But these are partials, right? The x and y things are partials because they have to be. And these guys are hard derivatives because they have to be, right? They're a function of one variable. In other words, like Chris says, there isn't a t direction, there's just t. You guys all see that? Okay, so this is the chain rule type 1, kind of. Right, where there's one variable controlling everything. This is the like a la calc 1 sort of. Right, because you guys could do this problem even in calc 1. You just make this substitution and then take this derivative. You would get the same result. Cool? So just throw that in your head. Okay, second chain rule, part 2. I'm gonna dump this. So what if we had f is a function of x and y, and x is a function of, say, s and t, and y is also a function of, say, s and t. That's cool, this. So I have maybe temperature in the room is a function of the density and the pressure or something. And then the pressure is a function of like time and the amount of poison gas. And this thing is a function of, right, now the other variable there, right, the pressure is the function of time and also the concentration of poison gas. Cool? You guys see how this could arise, at least vaguely? Okay, so now I'm not even sure what symbol I want. So I want like F with respect to S. That should make sense. Like if I change the amount of poison gas in the room, something should affect the temperature. What category of derivative should this be?
Partial? Good,
this should be a partial, right? Okay, and how should I calculate that partial?
I'm assuming you do the same thing, but you also have, no.
So there should be a partial of f with respect to x, right? And then, so that's like the x slope, right, of f. And I should have to multiply by the
partial of x with respect to s?
Yeah, something like x with respect to s, right? And then it's got to be a partial y.
Because it doesn't account for the t.
Good, because there's another variable there, the t, right? And I haven't accounted for it. So this is just the change in x that occurs from s. I haven't accounted for t. And then I should have the partial of f with respect to y. And the partial of
with respect to s.
Y with respect to s. Okay, if you want a rule for not tangling the variables up, you can kinda half-ass, it's not really true, treat these like fractions.
Okay.
You guys see that? Like if I cancel the partial x's, I get df ds. If I cancel the partial y's, I get df ds.
Not exactly true because they're both one.
But,
Yeah.
right, what's wrong with that as a thought?
If they really canceled, you get 2 DF.
Yeah, you get kind of 2 of them, right? You guys see that? That's really kind of a way of accounting for the dimensionality of this space.
Yep.
You should get as many of these as there are dimensions in this first dependence. It's all cool with that?
Yeah, it's like room per pressure and then pressure per poison gas. So you think of it as the measurements, not as the variables themselves.
Yeah.
So that's, you're on the right path.
You guys okay with this? So this is just a trick, and all it does is tell you that you're on the right path if you kind of think about slashing these. And then you just need to account for all the ways that f changes. So can you guys write the partial of f with respect to t?
Yeah.
Yeah? Hopefully? So you should get the partial of f with respect to x times
Partial of x with respect to t.
partial x with respect to t, and you should have to add to that
Partial
Copy,
of x
paste.
with respect to y.
partial f with respect to y times partial y with respect to t. Cool. Have I accounted for all the derivatives this way? Yeah. If I wanted to do some kind of more complicated, horrible situation where I had, say, g depends on x, y, and w, and x depends on s and t and phi and theta, and
Oh,
y
yeah.
depends on the same crap, and w depends on the same crap. Can you do this?
Yeah.
Do you want to?
No.
Not really, but can you?
Probably.
Yeah, totally. Right, you just say you want partial of g with respect to theta, right? Okay, you list out the things that g depends on. So you do partial of g with respect to x,
Y.
partial of g with respect to y,
And respect.
partial of g with respect to w. And we're adding.
And then x theta, y theta.
Yeah, and then you need the partial of x with respect to theta, the partial of y with respect to theta, and the partial of w with respect to theta.
And do that 3 more times.
You guys call that? Yeah, so if you want the total differential, right? Your book sometimes asks for the total differential. They want all the list of all the possible partial combos, so you just do it. Yeah, what's up?
So, for however many variables we have in the x, y, and z, x, y, and w term, then we'd actually have that many different sections, basically.
Yep. Yeah, for every one of the first level dependencies, you'll have a rate of change, right? And then what you put after that should be the rate at which that variable changes with respect to the thing you're actually differentiating. Cool?
I think I solved it when I was doing the calculations in the back of my head. But if we do f, the partial of x, is that changed at all from x being a function of s or t, or does that not matter when just finding partial of x?
Okay, yeah, so things depend on where you evaluate them, right?
Yeah, so you only have to worry about the x and y in that the function given.
Yeah. So you guys see that I have these formulas, right? Which I would like you to kind of know the idea behind at least, right? I might ask you to conjure one of these up. And then when we're evaluating somewhere, then we maybe have to worry about exactly how these go. So let me pause this and we'll evaluate one.